So our next speaker is Christian Tchilikov from Semify GmbH, where he's a digital design engineer at Semify GmbH, which specializes in digital design and verification for ASICs and FPGAs. Semify's in-house product, SmartWave, is built on an FPGA system and is designed for professional testing of devices that utilize standard communication protocols. SmartWave was developed primarily using open source tools, and all verification of the system was done via Cocotb. And the title of the talk is Utilizing Cocotb for Efficient Functional Verification. Over to you, Christian.
Yeah. All right. Well, thank you very much for the introduction. So let's get right into it. So my name is Christian, as mentioned, and today I want to talk a little bit more about actually using Cocotb for some, let's say, real-world examples and provide some use cases that we actually had here at Semify and how we were really able to leverage Cocotb to decrease our verification efforts and to increase our productivity for verification. So in my talk, I want to focus a little bit more on some real-world cases. I think Philip did a fantastic job of actually showcasing what Cocotb is and how to use it. So let's get right into it. Oops, sorry about that. Okay, so as an overview, I want to present what Cocotb is really quickly and how it's different from some other offerings currently that are used in industry. Showcase a little bit about the Cocotb verification flow, and then compare that with the standard verification flow, and then compare that with our verification flow and what we do in-house. And finally, I want to actually give some example use cases of some module level verifications that we've actually done at Semify and how they were made much easier by using Cocotb. And then finally, I want to showcase just the power of Python over System Verilog for verification of some specific modules as well. So yeah, I don't want to step on Philip's toes too much. We all, I think, got a very nice introduction about what Cocotb is, but fundamentally, it's a way for you to communicate with the simulator with Python, where you can drive signals, monitor signals, and then delay the simulator from advancing. So fundamentally, these are really the three main things that you can do with Cocotb. And using these three main things, you can make some really sophisticated blocks that have some much more advanced functionality. And Cocotb, what I do want to highlight in this presentation is that it's designed to be really easy to use and set up compared to other models that are offered, and has very low upfront costs, which we'll see later on as well. And what sets it apart from other offerings? Well, primarily it's free. And I think this is really important, right? It's free and it plays very well with open source simulators like Icarus Verilog, which is what we use, as well as commercial simulators like VCS as well. But the fact that it's free and that it offers access to Python means that it can provide this object-oriented methodology, which you can bring into verification utilizing Python, of course, and that allows you to kind of simulate this UVM-like methodology for entirely free. So one of the big downsides of some of these commercial simulators is that even though they're fantastic, typically licenses for them will cost you, tens of thousands of dollars a year plus for a single license. So that definitely is a really big barrier to entry, and having very similar functionality entirely for free definitely reduces the barriers to entry for this software approach to verification. And additionally, as Philip touched on a little bit, there's a really nice ecosystem around Cocotb, which comes in the form of these libraries of third-party verification IPs. So this could be bus drivers or monitors, and they come as Cocotb extensions. And I'll talk a little bit more about this later in the presentation as well. So what does a typical workflow look like in Cocotb? Well, you have your DUT, as I already mentioned, then you create some sort of Makefile, and then you instantly jump right into it, create a Python file, and start wiggling signals. So I will go over this section quite quick because it was covered a little bit in the last presentation, but the slides are available online if you guys are interested. They'll be available after the event, so definitely feel free to take a look there. So, at a very simple level, we have a DUT, a 2 flip-flop synchronizer. For our case, it's only running on 1 clock domain, so it's like a 2-bit shift register. So here we can see the Verilog code for this, and this is what the circuit actually looks like. And then we make our Makefile, which is really quite simple. I personally really enjoy this about Cocotb. I know it will be changing to runners, but I personally really like the Makefile approach because of how straightforward and simple it is. We just specify a few things like our simulator of choice, which HDL we're going to be using, and then all of our different sources for RTL, and we're basically done with this, right? Next, we're going to actually make our test bench. So here we have the test bench where we start wiggling the signals. We import all the Cocotb libraries that we'll be using. And then, yeah, we reset the DUT, feed in 100 random samples, compare this with our software model here, which we write, which is basically just rewriting what the flip-flops do, but in Python. And then finally, we run it, and everything works great. And you guys here will notice that all of our tests that we had that were marked with the decorator are ran individually. In this case, a test pass, which is very nice. If certain assertions within your tests fail, they're going to fail. So apologies again for going quickly through this, but I feel like this was already covered. So I want to get to some more practical examples. So what does our Semify's environment and setup flow look like? Well, for basically the development of SmartWave, we've used these tools as follows. So we use Icarus Verilog for compilation and for simulation. And personally, I think Icarus Verilog is really nice because like other commercial simulators, it offers its 4-state logic, which is really quite nice to have if you ever miss resets or if something is ever left unconnected. You instantly see this in simulation. And you're not left guessing as to what went wrong, really. We use still Cocotb 1.9 with the Makefile approach, as I mentioned, and we do plan on updating to Cocotb 2 when this comes out. There's definitely, I think, some really interesting changes that will be happening, and I think it'll be even a more productive approach for sure. And then I think a big thing that we do, which is why Cocotb fits so nicely in our flow, is that we use Python for basically all of our scripting and gluing. And Cocotb fits in quite flawlessly into this flow. And then finally, we use GTK-Wave and Surfer for analyzing waveforms. And lastly, honestly, we only really use Xilinx as a generate bitstream button because we're still working with Xilinx-based FPGA platforms. So this is what our flow looks like, or our environment looks like. Maybe let's talk about how we then incorporate this into our flow and give some more practical examples as well. So as I mentioned, we use this flow for SmartWave, and I want to give just a quick introduction as to what SmartWave is, and how it's really relevant to Cocotb. And hopefully this will then make some more sense as to why we chose Cocotb for SmartWave. So fundamentally, what SmartWave is it's an FPGA-based waveform generator that allows for connection to really any sort of peripheral modules that communicate over standard protocols like I2C or SPI. And a recent feature that we introduced is that SmartWave can now act as an I2C slave device, and it can essentially emulate any sorts of sensors or actuators that you would like, and you can model this emulation through a RISC-V core. And I want to focus a little bit on this later and actually show how we verified this specific section and present some ideas as to why using Cocotb actually made it more efficient than doing a traditional system Verilog approach. And it's also nice to know that SmartWave is a bus-based system. So what this means is that the modules on SmartWave are actually implemented kind of like how peripherals are implemented in a microcontroller system. And then what this means that the verification is actually done through these register accesses over a bus. And yeah, it's done over exactly. So over register access on a bus. So this is kind of a little bit of an overview of the hardware side. I want to talk about the software side and really where Cocotb comes into play. So as I mentioned, the verification is done over these accesses over a bus. And SmartWave, the way that an engineer would go on to actually interface with it is over a Python API that we wrote, or through a web GUI, but we mostly use our Python API for our in-house flows. And what's really nice is that our Python API looks very similar to our verification flow. And then what this means is that we can reuse a lot of code that we wrote for verification to actually write our API then for other engineers to use SmartWave with. And this kind of goes in two ways, this reuse of code. So when we're writing our verification, let's say we introduce a new module into SmartWave, like an SPI unit or something, and we want to do some sort of interfacing over API, over SPI. We would write our verification in Python using Cocotb to drive this SPI module, essentially verifying it. And then afterwards, when we want to write our API, we can take this verification code that we wrote, make some minor changes, and it becomes our new Python API code. And then this goes both ways. So now if we ever run into a production issue or some sort of bug or anything, using our SmartWave API, it's very easy then to go to simulation and see what exactly went wrong because the code is so similar. And what this does for us is it makes the turnaround from design to verification really fast and really efficient. And of course, this wouldn't really be possible without Cocotb and having this really nice Python interface for verification. And so this is, yeah, a little bit about SmartWave. Let's go ahead and actually talk about how we verified then this sensor emulation system using Cocotb and why it was easier than using a traditional method compared to System Verilog. So what is our goal? Our goal is we want to integrate this sensor emulation system into SmartWave. So assume that it doesn't already exist, and we want to go about designing it and putting it in here. So what do we need? For this, we're going to use a RISC-V core, which is going to be the CV32E40X. It's a small open source RISC-V core. It's, yeah, really quite small, but very nice and powerful. And it's notable that this core uses an interface developed by the Open Hardware Group called the OBI interface for any sort of communications. But the rest of SmartWave actually uses Wishbone. So all other peripheral modules on SmartWave are Wishbone based. So this, of course, introduces some sort of problem, right? We can't communicate with the core to the rest of SmartWave without some sort of translation that we need. So then we need to create another module that's going to sit in the middle. It's going to be sandwiched between these two peripherals. And that's going to be an OBI Wishbone bridge here. That's going to do the translation from one protocol to another and back. And then finally, we can take these three modules, put it together, and we'll have our sensor emulation system ready. And if we look at the picture here, we see that there's certain modules with checks and others with X's. The modules with checks, which is just going to be this RISC-V subsystem here, means that it's already pre-verified. So we take this IP from the Open Hardware Group and we drag and drop it into our system, assuming that it works. So we won't be doing any verification on it. Additionally, with the other two modules, we're going to make this OBI Wishbone bridge from the ground up, and we want to verify it, of course. And we're going to make this I2C slave from the ground up as well. But we're only going to verify the generic register file, which is on the left-hand side. This is what actually interfaces with the Wishbone communication. We're going to assume for now that the protocol decoder, which is what does the I2C side communications, works as intended. We're going to keep things simple just for this example, and we're not going to touch that for now. So what was our approach to this? Well, we have two modules that we need to verify. So we're going to start off by verifying both individually on a unit level. And we're going to start off with a bridge. And the way we're going to verify the bridge is essentially by sending transactions from some sort of OBI master. It's going to go through the bridge. It's going to go to some sort of Wishbone slave. The Wishbone slave is going to respond, and then the core should, if everything works, get this response. And we're going to verify that this flow can go all the way from one module, pass through the bridge, go to the endpoint, and then return back to the starting point. And if this works repeatedly, then we can have some sort of confidence that the bridge is working as expected. So as mentioned, then we need two essentially modules to verify. We need some sort of OBI master, and we need some sort of Wishbone slave. And this is where our first taste of Cocotb and the power of Cocotb comes into play. And this is through the form of these Cocotb extensions, which is not supported directly by Cocotb, but it's a very nice environment, which is kind of community driven, with a bunch of third-party VIP or verification intellectual property, where people can make these open source modules with the intent of verification and reusing verification. And just by chance, there's actually some for Wishbone. So for Wishbone, there is VIP for the slave module, which we're going to use, and we're going to drag and drop it on the right side of our Wishbone bridge. So this slave will receive communications, and it's going to log all of the transactions that it receives, and it's going to respond back to any requests. And on the left-hand side, on the OBI side of things, I wasn't able to find any OBI VIP. So of course, then there's potential for you to make your own VIP and publish this to the Cocotb ext system. But for now, let's say we want to bring this design up as fast as possible. Let's say we're on a little bit of a time crunch. We're just going to use already pre-verified IP in the form of just using the core itself as an OBI master, right? So then what does the workflow look like for this approach? Well, we can generate some test vectors using Python, which is going to be nothing more than a bunch of reads and writes over Wishbone. We're going to use our core as the OBI master, as I explained earlier. And then we're going to use this pre-verified IP, or sorry, this verification IP, which is going to be the Wishbone slave VIP, and it's going to respond and log everything. And then finally, we scoreboard all of our log transactions with all the generated test vectors. And for the core, here we also use Python to generate a very, very simple C program, which is just going to be the sequence of reads and writes. And we're going to call the firmware compilation script within Python as well. So really everything is going to be in Python. The entire flow from start to finish is in Python, and I think this is really nice. Also, we're able to leverage some pre-existing free IP And this really means that the only additional verification effort is to glue everything together, right? So the core already exists, the wishbone slave VIP already exists. So all that means is we have to put everything together, and this is all glued together with Python, which I think is really nice. Great, so we're done, right? Well, almost. So we ran this random test and we're able to cover a lot of cases, but of course we still need some sort of directed tests for certain edge cases, right? So I don't know if you guys remember, but earlier I showed that this core is actually running on a different clock speed with the rest of the system, so it's running a little bit slower. So there's still some considerations that we have to take, like certain reset domains within the bridge or these multi-cycle paths that you'd get from the core. But this is unavoidable, right? So this isn't a shortcoming of Cocotb. No matter how you choose to verify your design, you're going to need some sort of directed tests to really cover all the cases. But the nice thing is that we write these directed tests in Cocotb as well. What this means is that they're automatically added to our regression and they're ran with our random tests. And this comes in the form of just adding a few extra Python functions into your main Python file that you have. You add your Cocotb decorator. You can share any sort of intermediate functions between tests that you write. And this is really quite nice. It integrates into the flow very seamlessly, I would say. And finally, let's then verify our I2C slave module, as mentioned earlier. So we do a very similar approach. We're just going to take this wishbone master VIP, which is also provided in the Cocotb extensions. And we do the same thing, right? We generate some test vectors, we read out the register file, and we scoreboard everything together. Great. So if this is working, we can assume that we can put the entire system together and everything should work. So this is exactly what we'll do. We put the entire system together and we decide that we want to monitor all sorts of wishbone transactions going forward, right? So in this picture, there's only really one wishbone slave module, which is going to be this I2C slave. But in SmartWave, we have many more modules that are connected via wishbone that we would like some sort of way to monitor all wishbone transactions that happen. And this is where the wishbone monitor comes into play. So there's a little bit of a problem, right? Because Cocotb extensions, at least the ones that we found for this specific wishbone interface, let's say, they don't actually provide a monitor. But really, it's not so big of a problem because the IP in this case is fully open source. All the code is available. You can modify it as you'd like. What we end up doing actually is just taking the wishbone slave VIP, which already logs in all transactions, modifying it slightly, changing the handshaking signals a little bit, and we make a monitor out of it. And really, with very little efforts, we're able to take something existing, modify it for our specific use cases, and integrate it directly into our system. So what I hope that you guys took away from this is that the ecosystem around Cocotb is really, let's say, supportive of encouraging these fast turnarounds and encouraging reusability of code. And this could be really quite beneficial for upbringing any sort of design that you'd like and really finishing off verification quite fast. So I showcase a little bit about how we use the IP, but let's showcase the power of Python a little bit as well. So in this case, we have a specific component that we want to verify that's going to be a little bit more complex. And this component is going to be the eviction unit of a set associative write-back cache. And all this eviction unit does fundamentally is it takes some sort of input, and based from this input, it's going to output a specific way that is going to be evicted. And this all sounds like some mumbo jumbo maybe to some of you, but what you really need to understand is that this eviction unit, all it can really be thought of as is this binary decision tree here on the right, where these ways that I mentioned, all they're going to be is leaf nodes on these binary decision tree, and all the intermediate nodes way, and this way that's being selected. So for example, in the simulation case, it's wave 0. It's going to be the way that's going to be evicted next. So right off the bat, right, this is a data structure which is not so straightforward. There's definitely some complexity here. We have to simulate this in some sort of efficient way. And there's some additional complexity that's added because of the fact that this cache is going to be parameterizable. So ways here, these leaf nodes can be configured to any arbitrary number. So it could be 8, it could be 1024 if you have some sort of fully associative cache or some sort of victim cache or something. And this adds complexity, right? Because our verification needs to be able to handle this in some sort of dynamic way, ideally, right? You don't want to write these specific models differently for every single configuration. This would be kind of impossible. So we need some sort of way to generalize this as much as possible. So this is exactly what we do, right? This is where power of Python data structures are much easier
Yeah, I think we're getting problems, aren't we?
System verify is possible, but it's a little bit tricky, at least from my experience. And this is kind of exactly which Python is able to even use some existing libraries to work with these trees and to really elegantly print these data structures for debugging. And these, of course, any pictures can be printed and shown, and you could see a nice visual representation of what went wrong. And I think this is a really nice use case, right? If you can simplify your life in debugging, you absolutely should, in my opinion. And so this is kind of, yeah, one example of where, two more examples of the Python. These are a little bit abstract. Matrix, for example, you implement your hardware for this matrix multiplication. Code to do actually not in system verify, use Cocotb. You can really level up on Cocotb, and your golden model becomes one line of code, which is just going to be using the NumPy library and calling multiplication function within it. And this is really quite powerful, I think, where you can significantly reduce.
Hi, Krishnan. Sorry to interrupt.
You can
There's a
significantly
network
reduce the
issue.
amount of effort you have. Yep. Okay.
There's a network issue
Yeah.
from
Where
your...
did I leave off? Oh, sorry about that. So can you guys hear me all right?
It's just intermittent, so just carry on, Philip. But just if you can get a better connection.
Okay, yeah. Sorry about that, guys.
Okay.
No way.
Okay, that's all right. Thank you.
Sure. Okay, there we go. So yeah, that back to what I was saying though. So if we can reduce the amount of verification efforts that we have, and let's say reduce the amount of effort to create already existing things from other tools, I think this could be very beneficial.
Kristen, your screen is not visible actually.
Okay. Yeah, I'm having a little bit of issues. It seems like. Can you guys see my screen right now or no?
I
No,
think you
Krishnan,
have.
it really does look as though you've lost a lot of bandwidth somehow.
Sorry, one more time.
You're just in the final straight as well.
Yeah,
It's still
exactly, right at the home
loading.
stretch, right?
Okay, Kristen, could you tell me which
maybe I'll stop sharing and try.
No,
again.
which slide you were? Can you just tell me?
Sure,
I will just
I'm on slide
quick.
20 at the moment.
We've got it now. We've got it now.
Yep, that'd be great. I'm on slide 20 at the moment. Yeah.
Yeah, can you make it full screen, please?
Yeah. Sorry, 1 second. The good thing is I am almost done, so hopefully this doesn't block too much. But can you guys see everything?
No, these should.
No, I will share my screen quickly. I'm sharing. You can start speaking.
Please share, yeah.
Let me know if you're able to see my screen.
Yeah, go ahead, Tisha. Okay.
Kristen, you're able to see? Kristen, are you there?
Okay, do you want to go to the final slide? Just go to the conclusion, Tisha. Next one. Okay, so I think it's probably best if we stop there, because obviously we're getting a few issues. But I think we've got a good view of the way Semify use it and the way Christian uses it. There's some contact information there. If you wanted to contact Christian as well. Okay. Obviously, we can't give any questions to Christian, but there were a couple of questions for Philip, which he's answered separately as well. And I'll just read those out and tell you what the answers are. There were some issues around people with experience print on model sim. And I think Philip's just saying that sometimes it's buffered, so you have to be very careful about trying to write out to model sim from Cocotb because of buffering. And the other one was comparison System C, because obviously a lot of people use System C as a verification environment, which is a lot more software oriented than some of the VHDL and System Verilog environments. And Philip saying their system C is much more suited to high level modeling and high level synthesis, whereas Cocotb is much more suited to a test bench style environment. Okay, so apologies for the technology worked up until that point. Okay, thank you, Chris. I don't know if you can hear us, Christian, so we are going to thank you.